Whenever we apply an external force to a solid, a change in volume or shape of the solid can result. This change in shape or volume is called deformation. Elasticity is the ability of a solid to return to its original shape and volume when the deforming force has been removed. An elastic solid, therefore, is a solid which returns to its original shape and volume when the deforming force has been removed. Elastic solids are said to undergo elastic deformation. We also have plastic deformation, which is said to occur when a solid is subjected to enough force to make it change its size or shape permanently or irreversibly. Now that we know what elasticity is, and we know that applying a force to an object can cause it to deform, let's talk about how the quantity of the applied force relates to the amount of deformation the object experiences. Let's say we apply a pulling force, and let's call that pulling force F, to a wire of initial length L0. This produces a change in length of the wire. Any further increase in the force would cause further elongation of the wire or further change in length of the wire. If we recorded the values of force and the values of the elongation or increase in length of the wire, and we plotted these values of applied force against the elongation, it would give us a graph that looks something like this. On the graph, from the point of zero force and elongation to another point called the proportional limit, we can see that the relationship between the force and the elongation is a straight line relationship. And that means that the elongation is directly proportional to the applied force, or that the force is directly proportional to the elongation experienced by the wire. We can write this relationship as F equals KdL. Now, within the proportional limit, the wire remains elastic. This means that if we removed the applied force from the ends of the wire would go back to its original length. Further along on the graph from the proportional limit, we get to another point called the elastic limit. Within the proportional limit and the elastic limit, the wire still remains elastic, but the relationship between the force and the elongation is no longer a straight line relationship. So we can call the region between zero force and elongation to the elastic limit the elastic region of the material. Beyond the elastic limit or elastic region of the material, we have the plastic region. And in this region, any deformation of the material or of the wire is permanent. So if we removed the applied force, it would remain as the length it currently is. Finally, if we continue increasing the force, we get to a point called the breaking point. This is when the object fractures or breaks due to excessive force applied on it. Just a reminder before we move on that our relationship F equals KdL is valid for any elastic material within the proportionality limit only. The stress on a material can be defined as the force per unit cross-sectional area applied on that material. And the strain of a material can be defined as the extension per unit length of the material. This definition of strain only applies in simple cases such as tension and compression, but may have a different definition when it comes to shear strain or bulk strain, which we are going to discuss later in this video. For an elastic material, there is a relationship between the stress applied on it and the strain it experiences. And this relationship is given as Hooke's law, which states that the strain of an elastic material is proportional to the applied stress. This law mostly only applies within the elastic limit of the material. So far, we've only considered tension or tensile stress as a form of deformation an object could experience. But there are other types of deformation or stress conditions that an object can be subjected to. A different type of stress condition is compression or compressive stress. And this occurs when the applied force at the ends of the material are directed inward towards the material, giving a compressive effect on the material. Both tension and compression can be described mathematically by applying Hooke's law. If our strain is proportional to our stress, we can say that strain equals the inverse of E multiplied by our stress. E is a constant known as Young's modulus, and we can rewrite it to be equal to the stress divided by the strain. And so we can write E equals FL naught divided by ADL, where F is the applied force, which could be either tensile or compressive. L naught is the original length of the object, A is the cross-sectional area of the object, and dl is the extension or change in length of the object. We also have shear stress and strain. An object experiences shear stress when we have two parallel but opposite forces acting parallel to the face of the object on both sides. The effect of shear stress doesn't necessarily change the volume of the object, but changes the shape of the object by causing adjacent layers of the cross-sectional area of the object to slide over each other, and this effect is known as shear strain. We measure shear strain as the angle theta as shown. Applying Hooke's law to this, we can say that the strain is equal to the inverse of G multiplied by our stress. G is a constant known as the shear modulus or the modulus of rigidity. We can rewrite G as being equal to the shear stress divided by the shear strain. The final stress condition we're going to consider is bulk stress. If an object is subjected to forces from all sides, it's going to experience a decrease in volume. An example is an object submerged in a fluid. In this case, the fluid exerts pressure on it in all directions, and pressure is defined as the force exerted by fluid per unit area. So we can say the stress on all sides experienced by the object is equal to the pressure of the fluid. Again, using Hooke's law, our bulk strain is proportional to our bulk stress. Our bulk strain is equal to the change in volume of the object divided by the original volume of the object. And like we said before, our bulk stress is equal to the pressure or the change in pressure that the object experiences. So we can write del V divided by V naught is equal to negative of the inverse of B multiplied by dP, where dP is our change in pressure. We have a negative sign here because an increase in pressure causes a decrease in volume, and a decrease in pressure causes an increase in volume. So there's also a negative relationship between the change in pressure and the change in volume.